Exercise 1, mathematical induction, series type. Now we've proved by mathematical induction that 1 on 1 times 3 plus 1 on 3 times 5, etc. over 1 over 2n minus 1 times 2n plus 1 is equal to n over 2n plus 1 for n greater than or equal to 1. Now first of all, we'll take the case for n is equal to 1, and we'll prove that very simple little case. Now the left hand side is equal to 1 over 1 times 3, and of course that's just a third. The right hand side, this one over here, is going to be 1 over 2 times 1, which is 2 plus 1, and that is also equal to a third. Therefore, the statement here, we'll asterisk that statement there is true for n equals 1. Now what we'll do is we're going to show that this is going to be also true for some other value k. This is a variable k, some constant, so further down the track, so k is maybe 10 or 11, but k stands for some number further down. So all we need to do is actually rewrite all this line and replace the n with k. So we'll just do that. Okay, and I've done that there. Now I'll just label that A for the assumption statement. And we'll be referring to that a bit later on. Now what we have to do now is we have to prove the statement up here is true for n equals k plus 1. Now if we can do that, we can then go back to our original statement here, 1, and because we've shown it's true for the next term on, we can say, well then, if it's true for 1, it'll be true for 2. If it's true for 2, it'll be true for 3, and so on for all values of n. So this is the essential part of the proof, and I'll call that P. So now I've got to rewrite this, and we're going to add an extra term on. So I'll write that again. So that's 1 over 1 times 3 plus 1 over 3 times 5 plus, and you see there I have it. I've just replaced the, back in here, to get the next term on, I've replaced the k with a k plus 1, giving 2k plus 1 here, and putting the k plus 1 in there. That makes that 2k plus 3, and similarly on the other side. Now that's what I've got to prove. Now notice I put that in yellow, because you notice that all this part here is the left-hand side of the statement A. So what I'm going to do, I'm going to add that to both sides of this statement. All right, add it to both sides of this statement, and we'll see what happens after that. Okay, now you see that I've done that. There's the statement up here, A, right, and the yellow part here is what I had to add to both sides of it. Now you'll see now that the left-hand side here corresponds with the left-hand side of the statement P. So all I need to do now is to show that the right-hand side of P here is equal to the right-hand side of this new statement I've just made up by adding this to both sides. So we'll just write that out. That's what we've got to prove. Okay, now prove that now here we got it, this one here, that k over 2k plus 1 plus 1 over 2k plus 1 times 2k plus 3 is equal to, that's this one here, is equal to this one. Of course the left-hand sides match up. Right, now this is where the algebra comes in. Now, we'll look at the left-hand side. The left-hand side Let's rewrite it again. K over 2k plus 1 plus 1 over 2k plus 1, 2k plus 3. Okay, now you'll notice we need a common denominator of 2k plus 1 times 2k plus 3. So multiply numerator and denominator by 2k plus 3. That becomes 2k plus 3. This becomes 2k plus 1, 2k plus 3, plus 1 over 2k plus 1, 2k plus 3. Okay. Okay. Now we'll just remove those brackets. So it'll be 2k squared plus 3k plus 1 all over the common denominator of 2k plus 1, 2k plus 3. Okay. Now when you factorize that top line, you get 2k plus 1 times k plus 1 all over 2k plus 3, which becomes, 2k plus 1 here. Okay, now what you can see now is that the 2k plus 1s cancel out, and you get k plus 1 over 2k plus 3, which equals the right hand side of that statement P. Therefore, we know that the statement is true for n equals k plus 1. Now, we've already shown that the statement is true for n equals 1. Therefore, by mathematical induction, or MI, the statement is true for all n greater than or equal to